He speaks English. His Hebrew is not that well.
No.
Not yet.
I can speak in Swedish, but I don't think that would help very much.
Okay, so welcome to our Sandwich Club and our IL Tech Talks forum meetup. A few words about what are we trying to do in these kind of meetings. So we're trying, in LivePerson, we're trying to connect between people, and this platform of Sandwich Club or IL Tech Talks is a platform to connect with technical people about technical ideas. People can learn from each other, and more than that, developers can come with their ideas that they want to share with other people, and tell others that they're willing to hear. And we brought this platform to help people learn. And I have the list of in the last year, in 2012, we had all these sessions here in LivePerson. Like almost every month, or more than one, sometimes more than one in a month, we had some interesting lectures. Some of them were internal people here for the internal audience. Some of them were part of the IL Tech Talks meetup. We brought sometimes people from outside. Sometimes people from us were presenting like we do it today. And sometimes we were joining with other meetups that are not related to IL Tech Talks. And today, Byron will speak about, he will present in a minute.
Stuff and things.
A lot of new technologies that we're using, and Byron is our chief data scientist, right?
Yep, I think, last I checked.
Yes, so go ahead.
Okay, thanks, Ron. So, like Ron said, I'm a chief data scientist here at LivePerson. So I'm a statistician by training, but an engineer by vocation. So I started out late 90s working on a human genome project, back when big data was 2 terabytes, maybe 3. And I've been pretty much doing that ever since, from microarrays, and spend a lot of time in life sciences, and then ad technology, and finally here at LivePerson. So today I'm going to talk about some stuff we've been doing very recently here at LivePerson around real-time data. So our customers are we help them engage with their customers while they're on their website. So they're interested in, a lot of times, what's happening right now, because there's usually another human being on the other side of that visit, and they'd like to know what people are saying, how they're saying, are they angry, are they happy, is there some new topic that is coming up and they need to prepare their call centers for that information. So we've been trying to help them do that by collecting data in a more and more real-time fashion, especially as things like Twitter come around and now people expect real-time data, and then delivering that. So one of the prototypes we have is something we call internally Barracuda. So this is liveperson.com that you're looking at. It's live. It should tick over in a couple of seconds as things go. Maybe we have to reload. Nope, it ticks by itself. Okay, great. So this is actually live data that's coming in. So as we currently have 3 chats ongoing right now, and after about 5 seconds, the data arrives here, and we're able to process that information, display it. We can put up a word cloud. We can calculate handle time. We can calculate the number of visits, who's online, and things like that. And we built this in a relatively lightweight way using a bunch of technologies. We're fully buzzword compliant with Kafka on the back end, Storm in the middle, and nodejs and d3 on the front end. So everyone's favorite brand new buzzwords. And so I thought I'd talk about how we'd actually build it. And I think rather than just describing the technologies, what I'd like to do is I'd actually like to build one piece of this while we're here, and so we can see front to back how it's done using all the technologies. So the piece we're going to build is the word cloud. It's sort of a natural thing, and word counting is, of course, the hello world of the big data universe, right? You go to the Hadoop tutorial, you go to the Storm tutorial, what's the first thing you do? You count some words. So let's count some words. But first, let's talk about the stack a little bit. So just so everybody kind of if you've never heard the words before, you kind of understand what each piece does. So the first piece I mentioned was called Kafka. This is a data motion piece. So its job is to get data from point A to point B in a reliable way. It was developed at LinkedIn to replace ActiveMQ when they broke ActiveMQ. Pretty brutally when they tried to stuff 10 billion messages a day through it. Did not like that. So they simplified the model down, so they have this simple producer-consumer model. And we'll talk a little bit more about how it works in a second. Then we have Storm, and in this case Redis as well, which is streaming data processing. So you can think of it like Hadoop for streaming data. And it was developed by this company called Backtype, which was eventually acquired by Twitter, and now runs Twitter's streaming analytics, especially if you've ever used their advertising interface. This is what's backing it up. And it's more of a framework than anything else. It's for managing distributed computation. For those of you who remember the bad old days of things like MPI and the pain and suffering that is involved in distributed computation there, it helps a lot with that. Node.js is server-side JavaScript. So it uses the JavaScript engine from Chrome and attaches it to an eventing framework, EventD usually, sometimes KQ. And you can use it to write web servers, whatever you want. And it's designed to handle very large numbers of connections with relatively small resources. So it's perfect for this sort of application where it's a streaming application with real-time data. We're going to be holding connections open for a very long time, but they'll be primarily idle as we're waiting for data update. And then finally, D3, which stands for Data-Driven Documents. This is a JavaScript library. It's similar in many ways to jQuery, but it has a focus on connecting data to the jQuery processing. So everybody knows with jQuery, you select groups of DOM elements, right? So D3 is about taking that group of DOM elements and attaching it to data so you can manipulate it in a nice way, and we'll see how that happens. But let's get started. So first we're going to need some data, which means Kafka. I don't know why it's so small all of a sudden. It auto resizes depending on how high the resolution is. So Kafka has 4 parts. First part is the producer. This is pretty simple. This is the thing that generates data. So this would be your application server, whatever it might be, wherever your eventing framework is. The current protocol is really, really simple. You could actually implement it in raw sockets in Python in about 10 lines of code if you really want to. You don't have to because there's libraries for pretty much any language you can think of, but it's possible. Supports compression, snappy and gzip at the moment. And in the newer version that's not yet released, Kafka 0.8, they're making the framework a little bit more sophisticated so you can have guarantees about did the event arrive at a broker and so on. So producers write to brokers. Brokers are basically the data. They hold the data in a distributed fashion, so as you get more data, you can just add more brokers, and Kafka will distribute the load among each broker. The broker is essentially, for those of you familiar with databases, database internals is the write-ahead log from a database. It's an append-only file format that's persisted to disk, and then just holds it there for a specific amount of time, which is important. Kafka will happily eat all of your disk. If you produce more data in the retention time you've specified, then you have disk. And then it will just stop. And when you think about it, this makes sense, because Kafka's job is to not lose data. And so if you had a space limit that you could specify on the size of the persisted log, then you could hit that space limit very quickly and start dropping messages because you just don't have any more space. So it's best to have time and then manage the space as part of the standard maintenance process. So if you find yourself getting towards the end, it's time to add more disk or add more brokers, right? So as you add more brokers, each one will take on a smaller chunk of the data. Inside the brokers are topics. So topics are collections of similar messages that come from producers. So they have typically the same core format. They're all in JSON, they're all in Avro, they're all in whatever you want. Kafka doesn't care, it will transport anything. But generally speaking, they're all going to be something that the consumers can handle without having to do too much work. Most places, even LinkedIn, use a relatively small number of topics, less than 100 is sort of Kafka's design criteria. Some people have used it with tens of thousands, and it seems to work. But I think LinkedIn has maybe 5 or 6 topics. So they have one giant topic and then some metadata type topics that they use. And then finally, you've got consumers, and these are things that read the data. The consumer protocol is just as simple as the producer protocol. So again, if you really want to, you can do it with raw sockets, and it's fairly straightforward. But there are also just client libraries for everything that you might want to use, including, for example, Node. So, that's terrible. Let's see if we can. No, that makes it worse. There we go. We've tricked it. So let's start with, let's make a producer and generate some data. So I happen to have an XML file with the play Hamlet on my disk. And so I'd like to read that in and push it into Kafka so we can do something with it. So this chunk here, this is really just reading the data in. And then the actual Kafka, and then just to make it more interesting, so it takes a little bit of time, because we could read it in and push it out very, very quickly. I put it inside a timeout with a little bit of delay to make it look more like maybe, I don't know, chat back and forth. But here's the Kafka part, one line. So you just send and off you go. There's a little bit of configuration for you know, the host names of the Kafka producers and things like that. But normally you just point your producer at a Zookeeper instance, because Kafka uses Zookeeper to manage its brokers. And then you can auto-discover all the brokers that are currently live and keep track of live ones. And when they go down, stop using them, and so on and so forth. So you usually don't have to manage that yourself. You could, but you don't have to. So we'll write this to a topic called Hamlet, and off we go. So next we need a little consumer. How about we use the web browser for that? So this presentation is running through a little Node app. And so we'll just attach a little consumer to it. And it works kind of the same way. So when we attach to the consumer endpoint in the app, which we'll do through the front end in a second, we're going to use something called a server sent event, which is a relative of WebSockets. So it's a streaming service. It's actually quite well supported in browsers. So even IE, I think 9 plus, as well as Chrome, Safari. It works on the mobile browsers. It doesn't work on mobile Android, which is annoying, except for Chrome on Android, where it works just fine. So the default Android browser, no. The stuff you get from Google, yes. Weird, but true. It also even works on Firefox. And there's a shim out there where you can, there's sort of like a modernizer component. I forget who wrote it. So if you really need to fake it using polling instead, there's a little JavaScript shim that implements something that uses the same protocol, so you don't have to do any work. You can just include that as well. So what do we do? So in Node, the rec and the res are the request and the response. We turn the timeout as high as we can because there's no reason to close the connection. Nicely, server sent events will auto reconnect by themselves, so you don't have to handle this yourself. But you know, tearing down and setting up connections is pretty expensive from a latency perspective, so we'll just set it really long. We'll tell it we're about to write some event streams, so that's the text event stream MIME type. And now we're off. These are just a couple of helper functions to produce the output in the correct format. And here we go. We turn on the consumer. When the consumer gets a message, we will send the message function and write it out to the front end. And on the last message, so this is for managing the offsets. So the way Kafka works is it fills up a buffer with a monotonically increasing offset, and you can keep track, or you can have Kafka keep track, depending on what you want to do, of this offset, and that tells you the last message you've consumed. So if you want to do something transactional, you can actually grab the offset, read in some messages, try to do your transaction. If it fails, go back to your offset, but if it succeeds, update your offset and move on. So in this case, we're just updating the offset no matter what happens, because it's such a simple case. And then on the front end, this is it, pretty simple. So event source is the type of object that creates a server sent event. on the consumer endpoint. You add an event listener on message, that's the event that's produced. And in this case, when it does, we use some jQuery to update some DOM elements in the presentation. And here it is. So it's, let me restart the producer. And we can see it work. And there it goes. So it'll just do this, and we'll just let this run while we continue. So in the background, this is happening, this will be updating. There's some other things that are using it too. So, and that's all there is to it. It's really simple. And it was designed to be incredibly simple. Let's get back. So that's cool, but it's not really doing anything. And you don't really want to do everything on the client side. You don't want to ship all the data raw. So most of the time, we're going to want to process it. And that's where something like Storm comes in. So like I said at the beginning, Storm is really about distributed processing and a framework for managing those distributed processes. So it's made up of 3 parts. Well, really 2 parts, with the third part being the combination of the 2. So the first part are inputs, where data comes from, and these things are called spouts. I don't know how they got these names. You'll have to ask Nathan Mars. He's actually got a good presentation online about it. This is input data. In this case, we'll be using the Kafka spout, which is part of the contributed libraries of Storm. So Twitter actually uses Kafka internally as well. So they have a Kafka spout that they ship along with Storm itself. Things that do processing, these are sort of small units of computation, are called bolts, like lightning bolts. And these this data is transferred between spouts and bolts. You can hook bolts up to each other in the form of tuples. And tuples are just a serialized format that Storm happens to use internally. Kiro, I think, is the serialization format they use. But it's basically just an array of objects. Those objects all have an index number as well as a name that goes along with them. And we'll see when we start to use it how that works. And then you arrange these things in a topology. So a topology is just a way of saying, I want to hook this bolt to that spout, and that spout's going to output some stuff, and then this bolt will output some other stuff, and maybe it'll update a database. So I want to handle the outputs of this bolt and hook it together. So this depends entirely on the application you're trying to do. So we'll do a simple one here really quick. So for our topology, we're going to read that data in just like we did a second ago with the node consumer. On the inside, it's in a JSON format. You saw that when we parse it in the web browser. So we'll parse that. That'll be our first bolt, is the parser bolt. It's often your first bolt because you don't necessarily want to put that in the spout because then you'd have to modify the spout, and now you have all sorts of forking issues. And then we'll count the frequency of each word. And in the code, we won't talk about it in the presentation because it was just taking too long. But in the code that I'll put up on GitHub probably after Strata, also keep track of who was talking and things like that. So there's a little bit more complexity in the full code. But we'll go through just the word count part in this one. And we'll stash it in Redis to make it a little easier to manage the front end. Storm, you could hold it in RAM in Storm, and it has a facility called distributed RPC that you could use to query it from an external service. But in the production environment, you probably don't want to do that for 2 reasons. One is scaling, and the other is high availability. So you want to persist data somewhere where you can have some sort of replication, either master-slave or master-master style replication, so that if Storm goes down for some reason, your front end doesn't go down. The data gets a little stale, but at least it still works. You don't want a 500 because you're doing maintenance on the Storm cluster. So there we go. So first thing we have to do is configure the Kafka spout. So this is pretty simple. You do this at the beginning in the main of your setting up your topology. So topologies are built with a thing called a Topology Builder, fairly straightforward. And then you set a spout. You have to give everything a name. The names have to be unique. And we have this function, Kafka spout from args, which is a little utility function that takes in some command line parameters and then sets up a Kafka spout that points at the appropriate Kafka cluster with the appropriate topic. And that guy is actually not too bad. It's just, it's Java, it's boilerplate. So you get a list of hosts that you might want to look for Kafka. These are the different brokers. You could do this with Zookeeper as well if you wanted to. But in this case, we happen not to be. The partitions, usually this is going to be one, but Kafka does allow you to further partition the data beyond the broker level. So within each broker, you can actually have subpartitions. And all this does is it lets you have more threads reading. So if your consumer is bottlenecking on I/O, you can actually split the data internally and get more read multiplicity. And then this is just part of the spout configuration. We set some buffer sizes. We tell it it's going to be strings coming in as opposed to some other serialized format. And we create the Kafka spout with the appropriate configuration. So fairly straightforward. And then all we have to do is attach the bolts. This is not so bad, right? So yeah, the first bolt, like I said, is going to be the event parser bolt. So builder set bolt. We give it a name events. It's called the event parser bolt because I'm not very creative. And then we have to attach it to the spout. So the topology structure, you can think of it, if you're a SQL person, like group bys, if you want. So you can arrange for different bolts to be grouped in different ways. But if you don't care and you just want any bolt, because there could be more than one bolt of a particular type running, it depends on how much load you have, and Storm will figure that out for you. You can just say, you know what, any event can go to any bolt, and that's called a shuffle grouping. If you're familiar with Hadoop, it's similar to the partitioner. So the default partitioner is just to send things out completely separately. We do the same, so we have a word tokenizer, which we'll get to in a second. It takes in some extra configuration in the form of a Redis URL, but it works just like the event parser. The only difference is the event parser is producing a specific stream of data. So one of the interesting things with Storm is, like I said, a bolt can emit things as well, right? But it can actually emit more than one thing. So there's a default stream, which is what I have in the spout, but you can also name other streams that produce other bits of information. So for example, if you had a bunch of, say, events that all had the same format coming in, they were all, say, Avro or something like that, but then you wanted to split them up by type for processing because they represented different things, you could actually emit a different stream with a specific type of event. And in fact, in the full version in Barracuda itself, that's what's happening on the back end, because we have many different types of events. We have chat events, we have visitor events, we have survey events, and all these sorts of things. And they all go out in a separate stream. And other bolts that process specific pieces of information grab the stream that they want. And in fact, we're not doing it here, but you can keep adding different groupings. So a single bolt can subscribe to multiple streams at the same time, which is really handy if you want to do something like a join or something similar like that. And then the speaker one, that we won't get to the actual implementation, but it does illustrate a different type of grouping. So in this case, we want all of the events for a given actor on the stage to go to the same bolt because we're going to do some management of whether or not there's been activity. So in this case, we're using a field grouping. So the event parser bolt, which we happen to know from its documentation, produces a tuple that has basically 3 fields, a timestamp, a speaker, and a line like we saw in the first element. And so we want speaker to be the partition key. So a given speaker will always go to the same bolt for processing. And that's just if you need some sort of memory locality, like a local cache. For example, if it was something where you had to do a lookup in a database to grab some metadata about something, and you wanted to cache it locally so you didn't have to constantly hit the database, this would be a good way of doing that because you can make sure that the cache is always consistent on a given bolt. And you don't have to replicate it across all the different bolts. Otherwise, you'd have 3 copies cached on 3 different bolts if you had 3 bolts. So that's handy. And then off we go. So in the case of the word tokenizer, it's pretty simple. We're not doing very fancy tokenization. It's just white space delimited. So we just get the input line, and now you can see us using a tuple. And notice I use it. You can use it by index because they are just a list but they also have names. I prefer to use the names because that means I can move things around in the tuple, and I don't have to worry about screwing up, oh, now it's index 3 and instead of index 2 because I added a new field or something like that. If it becomes a performance bottleneck, you can, of course, ask the tuple what the index is and cache that and then access it by index if you want, because it's a little bit more expensive to look up by name. But it's also, I think, more clear in general. And we also grab the timestamp. These things are nicely typed, so you don't have to do the conversion yourself. The parser bolt can do that directly, and you only have to think about it once. And then we split the line up. And this guy here is our Redis library. So that's a Redis connection. And Redis has, so if you haven't used Redis, it's kind of like Memcache. It's a key value store, pretty fast. But it does have some nice higher level abstractions. For example, you have hashes. So you have a key value, but you have keys and values inside the value. So you get kind of 2 layers, which is nice because you can go request all the values of the hash in a single command, rather than having what you would have to do with Memcache is have, one entry that keeps the list of elements that is actually in the hash, and then you have to iterate and grab it that way. So it makes it faster to do that. It's actually doing some optimization internally, so it's far more efficient to use a hash than it is to use individual keys, as Tumblr discovered not that long ago. It also has arrays, so you can add things to the array, you can remove things from the array, sets, just like Java hash set, but also sorted sets, where it has a key that's some unique identifier, and then you can assign that key a score, and it will actually keep it in the database in a sorted fashion, which is nice because you can actually go through and you can ask for the 10 highest values. So for example, if you're, say, counting words, you could keep one of these arrays around that has the score is the number of times you see it, and if you want the top 100 words, you ask for the top 100 words. You could also ask what the score is of any individual element, both forward and backwards, as well as how many elements are between 2 scores, things like that. So it's got a fairly rich mechanism for handling that. And you can do kind of similar things with sets. You can always ask about cardinality, as well as arrays. So it makes life a little bit easier, and it's stuff that you'd have to do yourself in a more primitive key value store, but it does it for you nicely. Cassandra has a lot of the same features. It's a little bit more low level, so some of the abstractions, especially things like sorted sets, you kind of have to arrange you have to do them yourself with sorted columns and things like that. But you can do this in something like Cassandra or a Couchbase, any of these sort of NoSQLs. So we add the timestamp to the words, so it's basically building an inverted index for each word, if you want to think of it that way. And we also update this list here of updated words, which we'll use in a second to do some background transformation. So this is a pretty common storm paradigm, where you're doing some processing on something, and then periodically you're doing a much more expensive update and shipping that out to some persistence layer, in this case Redis. The newer versions of Storm, this is running on a slightly older version, newer versions of Storm actually have a tick event that can be sent to help drive that. So I do it with a timer, but with a new version of Storm, you can actually just set up a tick event, and whenever the tick event arrives, you do the more expensive update, and then you continue with your normal processing. That's kind of a neat new feature, but it's in 0.9, which is not released yet. So that update is here. So you can see I just have a simple timer that's running in the background, scheduled to run every second, that all it does is it looks at the words that were updated and then generates a word count hash that contains the counts of all the words we've seen. Why did I do it this way instead of just incrementing? So one of the things with Kafka, and actually any reliable transport system, is you have at least once delivery semantics. So counting becomes an interesting thing now. So rather than just incrementing, because you can receive the same piece of information more than once, you're essentially forced to do the cardinality check of a set, right? So you get a bunch of unique items, and sometimes they might be duplicated. So you actually want to keep track of the unique items not the total count of items, because if something goes wrong, you could get everything again. Now you've double counted everything and you can't back it out, which is why I'm using Redis, right? I'm adding things to a set, in this case a sorted set, just to make life easy, and then I can go back later. If I get the same message again, I'll add the same thing to the same sorted set, which has 0 effect. And so I can go back later and ask, okay, how big is this set right now? And that gives me my actual count rather than just incrementing. And that's what we're doing here. And we update a hash that just contains the counts of all the words. And actually, Redis has another interesting feature that is pubsub, which Cassandra can't have because of its design, but Redis can have. And what that does is it lets a client on the other side of Redis actually listen to a channel. And when this is updated, we send a message on that channel. The client gets told, hey, there's new data, and can go process it, bring it down, and in this case, push it out to a website. So this makes this fully evented structure really, really simple, right? Because Storm can actually now push things to the front end without being attached to the front end at all, right? They don't even know about each other. And there could be multiple consumers of that subscription service. So we do that here just to push things along. And we can also use it for rate limiting on things like updates, because we only update once a second. We know that at most we'll publish once a second, so we have sort of a natural rate limit in there. So that's the Storm processing, and it's currently running in the background since we kicked it off. If you're sitting close enough, you can probably hear the fan running in the background. But right now it's in Redis, kind of hanging out. Let's go take a look at it. So to do that, we're going to use D3. So D3 is sort of an interesting piece of software. We'll get back to Storm and looking at the output in a second. So it's similar to jQuery in a lot of ways. You select groups of things, and then you manipulate them as a group, just like you would with jQuery. In fact, it uses the same sort of syntax, right? That CSS style syntax, the selector syntax. So for example, if you did $span.word to get all the spans in your DOM with a word class, in D3, usually you have to select the body, and then you do select all span.word. That's sort of the equivalent. So when you see select all, think of it as the jQuery selector. But what you can do with that is once you've selected a set, you can bind data to it with the data command. So what that does is it takes all of the things that you selected in the DOM and lines it up with the data. And after it's done that, you now have 3 different types of things, right? You have new things, right? So these are data elements that don't have a corresponding DOM element. And you can get to those with a command called enter. So that says, you can think of it as elements entering the DOM, right? So if you want to select just that subset, you can use enter. You have things that are in the DOM but no longer have a data element, right? Maybe you remove something from the data array. You can get to those elements from exit. So enter returns a set of data with no element. Exit returns a set of elements with no data. And then if you don't do either enter or exit, you now have the set of elements that have both data and a DOM element already. And so you can use that to do all sorts of interesting things. So one of the things we can do is, let's say we're going to create some new elements, so that enter step, right? So I've got a little, if I can find my cursor, there it is, a little guy here it just is a data array that's producing a set of tuples that have an x and a y and a radius, and now I'm just rendering them out using SVG into a div. And you can see them appearing here. And the div is sort of about this big, and they just kind of keep appearing. So the code for that looks like this. So you can see I start with an empty data array. I cache the SVG, so I create the SVG surface to draw on. And then I set an interval with a half a second interval. And every time I add a new data element to the list, and I select all the event circles, bind it to the data, so every time the list gets bigger, there's always one new data element to add. Enter, and then I append a new circle I style it with some color and an outline. And then I give it a radius, a center, X and Y location, which I can get from the data. So everything in D3 can take a function as well as a constant value. And when it takes the function, the D3 will pass in the data element that goes with the DOM element that you're working with. So the DOM element is always this, right, the this token, and then the first argument to the function is always the data element that you've bound to it now. There's actually a second argument as well, which is the index into the data element. If you want to do something more complicated, then you can hold in an array. And then we do a little transition to set its opacity. So it starts with opacity 0 and comes up 1. So D3 has a nice, and it's well beyond the scope of the time we have. There's a guy named Vadim who works at a company called Meta Markets, actually just next door to LivePerson's offices in San Francisco, that has a 2-hour presentation on just D3 animation alone. It's on YouTube. I recommend it if you want to get like seriously hairy D3 rendering. Or Mike Bostock, who's now at the New York Times, is one of the other creators. And he has an entire website called Blocks, where there are more pieces of D3 example code for doing whatever you want. Any map you ever wanted to draw, he's a big map guy, is all on this site. You can go see examples there. But we'll just do something simple where we append some stuff. We can also do the element modification. So let's create some elements, and then let's just randomly move them around. So here you can see this is where we're not doing the enter. We're not adding new elements. It's always the same number of elements. We're just, apparently the zoom does some weird stuff. We're just moving them around in the space and updating them every half a second. And the zoom has apparently created 2 divs that are operating independently. It looks kind of cool. I like it. And so the code there is really, really simple, right? So we have the timeout again. We just go through each of the data elements. There happen to be 100 in this case. Choose new locations for them, and then you can see here where we go through an update. Right, so we didn't use enter, so it will only work on data elements that are also bound to a DOM element. And because we use the transition, we get the sliding back and forth. So the default is to just sort of linearly move between 2 states, but you can also set different, we could have made a bounce or something like that as well. And that's actually managed by D3. You don't have to do that yourself, which is really nice. And that's all there is to it. It's really simple to use. It's fairly low level, but if you go look at the examples online, you'll start to see higher order constructs, like things like graph axes, drawing paths, drawing lines, drawing bars, and stuff like that for doing, if you want to do more traditional data visualization, so bar graphs, line graphs, and things like that. And there are also a couple of packages. One's called NVD3, and the other one is called Rickshaw, that if you want just sort of out-of-the-box simple graphs, you're not going to do anything too complicated, and you don't want a whole lot of control, they provide sort of a nice getting started. You know, they can get you a bar graph and a pie chart. Please don't draw pie charts. But, that's kind of basic things. So now that we know how to use D3 a little bit, let's get that data out of Redis into the DOM, and let's make ourselves a word cloud. So this is actually the node server that we have been using. So you can see we bring in Kafka, we bring in Redis in 2 ways. One is in pubsub and one is in Redis, because the way the node Redis package works, if you can use a connection for the pubsub capability, but then you can't use it for anything else. I don't know why that is, but it is, and it's no big deal. So to handle the pubsub, when you switch into pubsub mode, you produce an event called message, just like kind of that event source stuff, that has a channel and a message. And we'll just keep an array of channels that we're currently listening to, or a dictionary of channels we're currently listening to that holds a function. And so when we get a message for that channel, we'll execute that function. So to get all the words out, you'll remember this from the initial configuration. I just copied and pasted here. Obviously, in the real version, you would refactor this out and do it all nice. And then the first thing we do is when we first get a connection, We call hgetAll, so that's hash get all keys. So that's what I was talking about, where it's a nice way of getting all of the subkeys in one big block, in fact, rendered nicely as a dictionary for you. If that succeeds, because remember, we could actually have started this before we started producing any data, so this might return null. But then we write it out. Dict is just in a hash in Redis, the value is always also a string, so it's a string-string match. It doesn't have any notion of type. Everything is always a string. So all dict does is it goes through the dictionary and converts all of the values into numbers, so we don't have to do it in the client side. And then we put our function, what we're going to do whenever we get that pubsub update from the other side. In this case, we're going to say we got an update, and then we'll just do the same thing over again, right? And send it out. So every time we get an update, we'll just grab that data and push it back out. Grab it, push it back out. And then we do the subscription. And we got through the play while we were waiting. But if we turn this on, there we go. We have a little word. So I'm actually using a little wordcloud plugin that decides how to lay out the word cloud. One of the things that D3 includes as part of its standard library is actually layout functions. So like force-directed layouts, or the sizes would also change, but we're running the same playthrough again, so the frequencies are going to stay the same. That's why it's not getting bigger and smaller. They're just moving around. But so it has a bunch of layout functions for doing things like force-directed layouts or tree maps and things like that. So and there's a whole other package of plugins that have other layouts. So one of the layouts that is available to you is something called it's like a spiral word cloud layout. So basically what it does is it randomly places each of the element, and then force directs them away from each other so they don't overlap, or they overlap as little as possible given the constraints of your space. This div is a little small because I didn't know about how much resolution I was going to have. So there's not enough space for all the words given the font size I've chosen. But it sort of pushes them all out away from each other a little bit. And it just does that over and over again. So I just have it for fun, not being stable. It's switched. That's interesting. Apparently SVG no like the zoom. Just to, so you know that it's happening. So it's basically every time an event is coming through, it's doing a relayout of the node cloud, and that's why you're seeing it moving around. Obviously, if you wanted to be nice, you could make it so the positions were stable and then the sizes just changed. So it's a little bit more subtle change, but it's more fun to look at in the demo. Then let me get my cursor so I can, where's my cursor? There it is. And so this is the code that does that rendering. So starting at the bottom, here's our event source again, just like before. Listening to the message. We're grabbing the data. And then D3 also has some nice data manipulation sort of utility commands. So what D3 entry does is it takes a dictionary, a hash, and converts it to an array of tuples where there's two elements, key and value. So it's basically, if you're familiar with Python, it's like the opposite of zip. And then d3.max finds the max. There's also an extent. So if you're doing axes and things like that, these all sorts come in handy. So we get the max value. And right, so we're looking at d.value, console log it out. And then this is the plugin. So this is just a piece of code that we set up here, where we told it how big the layout was going to be. It actually, you can optionally allow for random rotation if you want the word cloud to be even more unreadable. A font, what the font size should be, we're just going to use the size that we defined down here. And then after the layout is finished, so that's the event here, how to draw the layout. So here you can see I'm using all of both the enter, the update, and the exit features. So here, if it's a new word I haven't seen before, I add a new text element, give it a class word so that I can select it again later with text.word. I style it with the font size, which is right here. I then move it into its appropriate location with the transform element. This is an SVG thing. SVG is very similar to PostScript in terms of its rendering model. Translate it to where I want, and if I had rotation turned on, anything other than 0, optionally rotate it around. I set the text value itself, and since this actually comes from that original Barracuda thing we were looking at, in that interface you can actually click on the word and it goes to a search that uses that inverted index we were building to look up different transcripts. So you can do that here. So SVG elements are interactive, which is nice. You can do mouse overs, mouse outs, clicks, that sort of thing. Touch events as well. If the word already exists, of course, I just transition it to its new size and location. And if it's dropped off the list, which could happen, especially early on, right now it's in a stable mode, so that's not going to happen. We can exit and remove it, and it will disappear. You could put a transition on it, so maybe it fades out or something pretty like that. And then off we go. And that's pretty much all there is to it. So that's how this works. And that's kind of my bit. So if there are any questions, let's go.
How do you handle multiple data centers input to Kafka?
Kafka is actually pre-designed for multiple data centers. So there's a thing called mirrormaker, which is basically a tool for taking one Kafka cluster and mirroring it to another Kafka cluster across a data center line. You can, it's actually arbitrary. So I know for example, LinkedIn's structure is they have 2 active data centers that do their serving for their page. And then they bring both active data centers into a big Kafka in their data warehouse data center, which is a 3rd physical data center. And then their Hadoop cluster pulls all the data in from that giant Kafka. So they actually merge two streams together.
What about Redis in terms of multi-data center?
Redis has a less good but interesting story. So Redis doesn't really have, it has master-slave replication. So your masters probably all have to be in the same place, but you can have slaves in other data centers.
What do you do here? It's just in one data center?
Oh, actually this one, because it's a prototype and it's on a different domain, it's actually 2 data centers away. So we actually replicate Redis from the master as a slave to an intermediate data center. And then Redis actually has a feature where you can be a slave of a slave. And so then we then replicate the Redis again to the 3rd data center where the UI actually lives. So it's actually a 3 data center setup. And it actually works pretty well.
Is it working on large scale masses of data? Because if I'm not mistaken, then Redis doesn't have incremental replication.
Not yet. It's coming. But yeah, so if the link goes down, you have to do a full replication. And that can take a while, depending on how big it is. So hopefully one of these days they'll figure that out. But right now, we just wait when it goes down. The nice part is when it goes down, at least it doesn't die. So the data is still there, it's just stale. So it's not ideal, but it's better than the 500 alternative.
What about failures inside the storm? When you have an inbox and you have a storm topology or several pieces, and one of them, all the data that you have in one of the storm service phase. The storm processes phase, you don't have.
Yeah, and Nimbus will restart processes, but if you're holding.
But you have already read the data from the copy.
Right. So within Storm, it was in that execute step. You actually have an acknowledgement of a tuple. So what you can do is you can actually essentially set up transactions in Storm where you don't actually acknowledge the tuple until you've completed all processing. And so if the bolt dies before it's been able to process the tuple, it won't be acknowledged. And so the spout will actually resend it down the chain. So it has this transactional notion. They're making that more general in newer versions of Storm with the Trident DSL that handles that a little bit more naturally because right now it's setting up transactions is kind of a pain. because you have to like set up the anchoring and the act chain all yourself, and Trident kind of automates that a little bit for you. So
What is the impact on the performance?
obviously it does reduce performance a little bit, but you can always just add more machines. So if it matters to you to have that transactional capability, then you can choose to do it and pay for it in terms of machine load. So you just have to get more machines, right? For a given data load.
Are you using anchoring in this solution now?
In this guy, yes. In the example we just did, no.
Yeah, it wasn't an example. So
Yeah.
But it's part of your solution.
Yeah. So we're using anchoring here. So after you. The anchoring is primarily on the transcript, so we wait for the transcript to actually commit to Redis before we acknowledge the P line. We don't do it everywhere, so like visits, we don't bother to anchor because you miss a visit or two, who cares? It'll sort itself out eventually. It's an approximation anyway. But for something like a transcript where somebody might want to go read it, then we do. And that's kind of the nice part, is you can pick, right, about how much do I care about my data.
How do you deal with configuration changes? If you want to change a broker or whatever, do you
You do have to stop your producers or hold them in some way. Amahai over there and I argue about this a lot. There are a couple of ways of dealing with it at my previous company. The way we dealt with it and the way we're probably going to deal with it here is we actually had a local Kafka on each of our servers running embedded with our server itself. And then we used a more general version of the data center mirror to actually read in from the 1,000 or so machines. You have to make some modifications to do that because it's usually designed for a 1-to-1 connection or maybe a 2-to-1. But that way, if the main Kafka goes down, you have a little local Kafka that's caching, and it's doing the same persistence thing. So when this guy comes back up, he can go, as long as it's inside his persistence. Yeah, Scribe does something similar. And then Storm does okay. It doesn't handle rebalancing very well. You have to bounce the topology, but they claim that they'll be fixing that eventually. And on the front end side, actually, if the node server goes down, the event source stuff is auto reconnecting. So when we're doing development, we bounce the server all the time, and the front end continues to function with absolutely no problems whatsoever. So Redis is a little bit smoother about that.
Can you provide some more real-world examples of what you do in Storm? What kind of computation or what do you achieve there that you wouldn't be able to achieve with just code that reads stuff directly?
It's more about, Storm is more about the management. I mean, we could write all of this sort of stuff as individual processing, but then we'd have to implement things like the failover. So like the first question over here, if one of the worker nodes dies, the data is rebalanced to the other worker nodes without having to do anything, unless the Nimbus dies. But if there's a head in the thing called the Nimbus, if that guy dies, you can't rebalance, but you can bring him back up. So it's more about the management of those individual processes, sort of like Hadoop, right? You could use a traditional queuing system like Torque or DQS or PBS or one of these things and, separate out all of your data, split it out to all the nodes, go out, process on all the nodes, collect it all back, right? Something like MPI. But it would be a lot of work, and you'd end up implementing Hadoop. So in the same sort of scenario, we'd end up implementing, if we did it individually, we'd end up implementing a lot of Storm. So just let us get a head start on, Nathan already figures this stuff out. It works pretty well. It is a 0.8, so it's not, the most mature product in the world, but it gets the job done and gets us, we don't have to implement it all ourselves and make all the mistakes that he made over the last 2 years. So it's more about catching up. The actual processing itself, you could do that in pretty much anything. It lets you get to the processing instead of dealing with bureaucracy, right?
When I look at, we have both
and it enables streaming processing.
Yeah.
And if I look at the opposite, like Hadoop, which enables batch processing, with Hadoop I get data locality.
Yep.
And with Storm, it's not really not tied to any data store.
That's right.
So is there some kind of a way I can achieve data locality, or I just need to implement it myself? Like Gold has its own data store.
Yeah, that actually, so like data local type stuff that you're querying across is actually where the distributed RPC comes in, where you can have other things query out to, basically it's a mechanism within Storm, and it's not something special. It's not an added part of Storm. It's actually just a convenience layer for existing Bolt and topology construction. But it turned out exactly like you say, that there are often cases where you want to do some processing in your local Bolt and hold that data locally in RAM, and then have something else query all the bolts. So that's where essentially you're introducing your data locality in the stream, is you're keeping that cache locally in RAM, and then something else is querying and doing some final aggregation across all the bolts, which might be on different machines. In fact, probably will be.
But anything larger than my RAM, I need to have some, because if I need...
Yeah, Storm is designed for in-RAM processing.
Yeah, so anything else I would need to like, implement it myself. And
Yeah, I mean, if you look at the stuff the Storm guys have been talking about recently, they've had this Lambda architecture idea, where they're starting to hook up the batch processing to the real-time processing and make that smaller and smaller over time. But I don't think it's a well-baked idea at this point. I think it's fairly new, so they don't really know what they're doing there yet. There are other things like Spark from Berkeley that have more of that notion, because Spark is more like a faster distributed Hadoop, and there you have data locality as well. So you might just look at that instead as a different option, right? This is not the only tool that does this in the world.
Well, it's not really connected to what you just shown, but another question. Well, you have the word count with Storm.
Yeah.
You have word count with Hadoop.
Yep.
So now the question that might raise that why we don't have any abstraction that does it together and put it into one database, so I can drill in and say, okay, for the last one day I saw this information about word count, but for the history of 3 years history, I saw that information from Hadoop, which is much more real data, because I know that Storm might fall and it's not in RAM, it's not, I'm not sure.
Sure. Well, again, that's the Lambda infrastructure that Nathan's been talking about, where you can basically stream Hadoop back in through Storm.
Is there any abstraction that does that already? Because
Not really, because...
it needs to be something that someone needs
Yeah, I know what you're getting at. So the answer is not really, and the reason is, so in this simple example, we weren't doing anything complicated with the word counts, right? Because we're just looking at unigrams, single words, and even with all the languages in the world, there's just not that many words that people use. And in a real situation, we're filtering out gibberish, right? And things like account numbers. If it's all numbers, we'll probably just filter it out. If it looks like an email address, we'll filter it out. So there just aren't that many words in the world. But imagine the case where we wanted to look at phrases or something like that. So you want to look at all unigrams, all bigrams, right? 2-word combinations, 3-word combinations, 4-word combinations, up to say 10 words or something like that. That set's going to get really big, right? It's like a factorial type of set. And so there, you'd actually handle them differently in a real-time scenario than you would in a batch scenario. Because in the real-time scenario, speed matters. So, and so you want to be in RAM, and RAM is much more limited than disk. So you probably switch to like an approximate data structure, like a count min sketch or something like that. So these are these data structures that they act like sets in some ways. You can ask a specific question about them, but they introduce some error to gain you less RAM required to store it. So if you're keeping all the possible phrases in RAM, this could get really big really fast, right? Imagine there are a billion, you'd have to keep a billion entries in your hash table. This is, you can do it, right? You can buy a machine with 1.5 terabytes of RAM these days. It's expensive, but it's doable. But the question is, do you want to do that? Usually no, because it's not worth that much money. So there you start to say, okay, well, is there another data structure I can use that's much, much smaller and gives me an approximate answer? And yeah, it turns out there are. And you can go from, requiring hundreds of megs of RAM to, a few K for something like cardinality estimation. So I think people want that abstraction, but it turns out that real-time and batch are not actually the same. So I think you end up using them in different ways. It just happens that this case is so simple that they look the same. So when we go to the big boy version of this, they won't look the same.
Do you store a history over time?
Yes.
In Redis as well?
Yep.
So you can go back in time and see how
Yeah.
it looked like 3 hours ago?
So in this particular example, and we didn't do it in the example because it's just more Z-ads and things like that. We're keeping all the information at a 5-minute increment, so in slices of 5 minutes, the last 5-minute word count for 8 days, at hourly level for 30 days, at daily level for 90 days, and then we have some higher level summaries that are used for doing ratios that we keep forever.
And the 5-minute, the initial aggregation to 5 minutes is done inside Storm?
Yeah, actually, what we do is we actually update all 3 keys on every single pass, or 4 keys, rather.
And the lower retention periods are done externally?
Well, actually, we're using Redis has the, like Cassandra, has the ability to expire keys. So the expiration is actually totally handled by Redis.
Yeah, but do you hold the expiration in order to do the lower resolution aggregations, or is it an external process just us?
No, it's the aggregation is all done in process in Storm at the same time.
Everything.
Yeah, everything at once. Because the individual writes are all pretty fast. So we just, we're like, we could iterate and do that sort of thing, but it turns out it was actually just as fast to update all 4 at once. Yeah. And a lot easier from a programming point of view.
And do you store it on rounded increments or of intervals, or is it the last 5 minutes?
In this case, we're using specific time slices because that's what we wanted. But with the Z-range stuff, you can arrange for it to be over a rolling period. But there you'd use a secondary updater, to calculate that sliding window. But if you use timestamp as your score, you can ask for everything, over the last 5 minutes. And we do actually, for this stuff, we actually are doing that. Because that's actually, the way it's defined is defined over time, yeah. I heard 2 voices. I see your hand. We'll get this one over here.
You have a consistent amount of load coming into the system, or you have lots of peaks
in this case, it's not flat. It kind of, obviously there's a peak period and a low period, but it's not spiky. So it comes up sort of smoothly and comes down sort of smoothly. And if we were looking at the 5-minute increments, you would actually see that smoothness.
And just curious again, like during the time that you probably were still figuring out how much compute resources you need for all this pipeline.
Yeah.
Which of the components would usually break down first?
So until we got used to tuning Storm and figuring out how many workers we need, Storm was the bottleneck. These days it's mostly RAM in the Redis cluster because it's restricted to its RAM. So that's the thing that we have to watch. Fortunately, that's odd. Fortunately, there's stuff to do sharding with Redis. So there's a tool called Twem Proxy. I think it's also called Nutcracker, which is actually it's another Twitter tool that will manage sharding of keys. So that definitely helps manage the Redis load because you can set up multiple masters that are true shards and then slaves of those. The consumer then becomes a little bit more complicated, but if you shard on like the user ID, then any given user ID is always talking to the same cluster. But if you were something really big, like you wanted to keep the billion or so entries, and you actually wanted to keep all of them, you could then shard into each set, and if you did it on, say, the hash, like a partitioning type thing, these would all be mutually exclusive. You could do a scatter-gather type calculation. But yeah, Redis is the nervous-making one now. Now we have kind of a good handle on Storm, and Kafka is fast. And there was somebody else over here was asking something, or was that just like a cough? Amahai, it's your fault.
So have you tried to run analytics on the data that comes out? So I look at this at the stack of Kafka and Storm, like an ETL layer.
Yeah.
It just brings in data, you do some transformation, and then you do something. So in this amazing example, you visualize it.
Yep.
But I guess
that's the first step.
We'd like to make more complex things like analytics.
Yeah, so we're like, for example, one of the things we're playing around with this right now, it's under development, so there's nothing to show, is an anomaly detection tool that actually is, we were just talking about this the other day, where, okay, yeah, it's an anomaly detection tool where we actually have a bolt that is looking at the data as it comes in and comparing it to the historical data, and then seeing if there's a change in like word count frequencies and things like that. And that's actually where we're starting to use things like the count min sketch to
So you build models based on historical data, and then you analyze the real-time data. And
yeah, so at my last company, we had a little PMML based thing that we could build into a bolt and evaluate models on data that comes in. It's a little bit more complicated as you have to accumulate a state and something like that, but there's nothing stopping you. There's no technical restriction that says you can't do analytics. Most people, let's face it, most big data stuff is really just counting right now. So we're trying to move to the next step. And we were talking about this like an alerting type system or something like that. You could actually, like pubsub is great for that, right? So when you see the anomaly, you could actually pubsub the anomaly out and then report it on the front end very smoothly. So.
Another question for the counting issues. There is also, I've heard about the term of like iron count.
Yeah, so iron count is like a simplified version of this.
Yeah.
So it's a little bit faster if all you need to do is count, and it's definitely easier to set up if all you need to do is count, but it's not as flexible. So
Yeah.
we want to put
Maybe-
more
but
things in
maybe
there.
It's like for the stuff we see the Hadoop and the Storm,
Mhm.
the Hadoop for batch, the Storm for real-time.
And maybe iron count for
And
iron
the
counter.
count for the counter and Storm for some complicated real-time processing. And
Absolutely.
for batch is,
And that's that's one of the things that Kafka really enables well, is it provides a common mechanism for attaching all of these things. So you can have your iron count thing and your Storm thing and your Hadoop thing, and they don't really need to know about each other, except if they need to talk to each other. And if they need to talk to each other, they can just write back into Kafka and put it out. So that was what actually, if you go listen to like Jay Krebs or Jin Rao at LinkedIn, they were talking about the problem they were trying to solve. You know, back in the day, they had sort of the n-squared communications problem, where they were creating new services like people you may know and recommendations and this, and they were finding that all the services were wanting to talk to each other, and so every time you introduced a new service, you had to spend all this time like learning the protocol for their API and the protocol for their API and their API and their API, and they're like, well, why don't we just put it all into like a central thing and move it around that way? So that it actually makes that much easier. And then you can kind of use the tool as appropriate.
What do you do about the monitoring and deployment of Storm?
So right now,
Actually, but Storm, in terms of monitoring, do you use the internal monitoring?
not so great. Yeah, so we mostly use the internal monitoring right now. But there is a tool that I just discovered the other day, specifically for Storm Kafka monitoring. I can't remember the name offhand, but if you Google for the Kafka spout, it's like the third hit. And it's actually, it hooks into a monitoring system for monitoring how far behind the Kafka spout is from the actual Kafka offset. So you can tell if your Storm cluster is getting slow or not able to keep up and things like that.
And in terms of monitoring the actual bolt operations, do you send it monitoring data to an external system?
Yeah, we actually do it through Redis. Yeah, we pubsub status information because we're using New Relic, and we actually, one of our mobile team, one of those guys, he has an open source project called Popcorn, which is an Erlang monitoring server. So we're driving through Redis out to his Popcorn so we can do some monitoring there. So like, yeah, like performance information. So each of the bolts, everything is time-stamped. So we actually keep track of the skew between the time at the bolt and the timestamp on the events, and that's actually pubsubbed up, so we can report on it later. Figured, yeah, for reporting, we might as well do our own monitoring through our reporting system. Is that it? Awesome, thanks guys.